Welcome to the lecture on phase diagram of iron carbon system. So, we know that iron is one of the very important element and its alloys are mostly used. So, they are one of the most widely used materials for engineering applications. So, the metal iron is a primary constituent of some of the most important engineering alloys, and when we take iron as the element, so on that basis we call it as a ferrous material. So, in that category it comes ferrous materials. Now, if you talk about the pure iron, so it is an allotropic material. So, that that means that it can exist in more than one type of lattice structure depending upon the temperature. So, if you draw the cooling curve of iron, you will see that at different temperatures you will have different type of lattice structure of iron, and the different temperatures, if you try to find the cooling curve for the iron, so that will be something at different temperature. So, if you draw it initially, we know that its melting temperature is pure iron has melting temperature close to 1539 or 1540 degree centigrade. So, if you come to that, so if you are coming from anywhere from higher temperature, then at this 1538 degree centigrade or 1539 degree centigrade, you will have so the liquid will start crystallizing, and then it will up to, so you have about 1410 degree centigrade. So, what you get is in that you get, so in this case you are getting the delta type of iron. So, that is known as delta Fe. Further, when you are decreasing the temperature, so temperature will decrease, and then further you are getting in between you are getting the gamma iron. So, now here, so here you are getting gamma iron. So, we know that this gamma iron has the FCC structure, this has the BCC structure, this has the FCC structure, and then so this is of the order of, so this temperature is about 910 degree centigrade. Then below that up to 768 degree centigrade, so that in that case you are getting here, that is your alpha iron. So, and then further also you are getting the alpha iron. So, both these are BCC. The only thing is that this alpha iron is magnetic, and here it is non-magnetic. Gamma iron also becomes non-magnetic. So, that way this is the cooling curve for the pure iron. Now, when we talk about the engineering alloys based on iron, in that case the carbon is considered to be the most important material, because it is influencing the properties of the iron based alloy system most considerably. So, based on that you have you see the iron carbon phase diagram. So, that is why we need to understand the iron carbon phase diagram, and what happens that normally it is iron carbon, or because with the percentage of carbon variation you are getting the different phases. However, you have one intermediate phase in between, intermetallic phase is there at 6.67% of carbon, that is Fe3C iron carbide, or that is known as cementite. So, normally many a times we also call it as iron cementite phase diagram. Now, if you look at this diagram, what you see that towards the left hand side, so this is your carbon percentage which is increasing in this direction, and Now, what you see that this is your 1535 or 38 degree centigrade. So, here in between you have delta iron, then you have gamma iron, then you have now the alpha iron. So, ultimately when you start alloying this iron with carbon, in that case the you can see that the solubility of carbon is somewhat limited. If you take the solubility of carbon at the room temperature, it is very small, 0.002 percent. However, as we increase the temperature and as we with that the solubility of carbon will be changing, and that will also be different for the different types of allotropes, tropic form of carbon. So, suppose this is the gamma iron. So, here you can have the maximum solubility here close to the order of 2% at this temperature. Now, if you look at this iron carbon diagram, you see many kind of invariant reactions here. You have first invariant reaction if you look in the lower temperature range. Now, you see that this is one line. Now, in this case what you see that this is your alpha phase and this is your Fe3C. So, again what we have studied in the phase diagram, using the phase diagram when there will be phase transformation taking place. So, you can find out when there will be crystallization going on, when there will be solid phase coming out of the liquid one. So, by the help of tie line rule or with the help of lever rule, either you can find the composition of the phases or you can also know the amount of phase that is formed. So, this is your Eutectoid point. In the Eutectoid point what you see that this gamma, which is of about 0.8% carbon, now this is while cooling it will convert to one side is this alpha and another side is the Fe3C, that is cementite. So, this Eutectoid reaction will give you, and in fact at this composition the transformation which occurs. Now, in this case the alpha and Fe3C which you get, they are in the alternate lamina. So, there will be layers, and that alternate layers of alpha and Fe3C together we call it as the perlite. So, basically the austenite will convert to perlite, and this is known as the Eutectoid reaction. Now, if you come to the point left to this point, then it will be the pro-Eutectoid so the point this side, and this will be hyper-Eutectoid on this side. So, any so first of all when we combine the iron with carbon, and that too up to suppose say 2%. So, below 2% we call it as the steel or carbon steel. So, in that basically you have low carbon steel or medium carbon steel or high carbon steel. So, it will go maximum to 1.5% to 2%. So, that may be for the steel. Once the carbon percentage moves from here onwards, then we call it as the cast iron. So, cast iron is the one where basically either you can have the graphite as the so graphite will be there in the form, so carbon will be there in the form of graphite, or you may have also Fe3C that we will discuss later. Now, so you will have hyper-Eutectoid steels. If you have steel of carbon less than 0.8%, then it will be hypo-Eutectoid steel, and if it is more than 0.8%, then it will be hyper-Eutectoid steels. Now, what you see that this zone is alpha, and this adjacent zone will be alpha plus gamma, and this is your lower critical temperature, upper critical temperature. So, these are the critical temperatures they are known as, and you have this is the alpha plus gamma, this is known as the intercritical temperature zone, and this will be your the gamma, that is austenite, that is FCC iron. Then this is one of the environment reaction, and that reaction is nothing but the Eutectoid reaction. So, gamma will be changing to alpha plus Fe3C on cooling. Now, when there will be any composition of any percentage. So, if it is of the Eutectoid composition, then gamma will come up to this point, and after that there will be ferrite as well as the cementite coming out. So, after transformation, you will get the ferrite and cementite. If you come to any composition lesser than or towards the left hand side of this point, that is your Eutectoid point. So, when it will the temperature will reach below this. So, you will have formation of alpha, and that will be of this composition, and then formation of gamma. So, that will be according to this. So, that will go, and from here again you will have alpha and gamma. So, this gamma which is remaining, that will be again transforming to perlite or so. So, you will have ferrite plus perlite. Similarly, when you go to this side, you will have perlite plus cementite. So, for hypoeutectoid steels, you will have some proeutectoid ferrite also formed, because the ferrite which is formed before this, so that is known as proeutectoid ferrite. And you can also find the amount of perlite, amount of ferrite which will be there in this composition, that is in perlite. So, based on the Lever rules, you can find the amount of ferrite which is there in the perlite. So, basically if you go to for any the such composition, you will have proeutectoid ferrite as well as the ferrite attitude corresponding to the eutectoid reaction. So, altogether you can find the total amount of ferrite. So, that is how this phase diagram is made use of to find the different type of phases which are formed, and what will be the mass fraction or what will be the amount of proeutectoid ferrite or ferrite formed or perlite formed or so. Another reaction which we see in this case is after this temperature, you see one temperature, that is 1150 degree centigrade. Now, in this case what you see is that there is this point where the liquid basically above this point, immediately you will have this is a liquid zone, and once the temperature comes below this, you will have the mixture of two solid phases, that is one is gamma, another is Fe3C. So, this reaction in which one liquid liquid is converted to two solid phases, that is basically known as the eutectic type of reaction, and this is the eutectic point. So, this 1140 or 1147 degree centigrade, or sometimes you will also get 1137 also, at many places you will find it. So, this point is eutectic point, and on this you are getting the mixture of gamma plus Fe3C. As discussed, that when your temperature comes below this, then as the temperature comes below this, you will have on this side, this line is touching to this point, so that is gamma, and on this side you are touching this line to, this is Fe3C. So, you will have gamma of this composition and Fe3C of this composition, and that is a straight line. So, anyway there is no problem. However, the amount of gamma and Fe3C will certainly be according to the Lever rule, and the amount of gamma which is formed will be this upon this, that is a fraction, and amount of Fe3C formed will be based on this distance divided by the whole distance. So, that way you are getting the gamma plus Fe3C coming out. Now, when you come to this point slowly, so once you reach to this point, you know that you will have gamma of this composition. Now again after that this gamma will convert to perlite. So, you will have ferrite plus cementite, whereas this is basically the cementite itself, intermetallic phase it is. So, you will have the austenite further being transformed. So, this reaction is known as the eutectic reaction. If you take any point left to this, it will be a pro-eutectic point, and if you take any point right to this, it will be hyper-eutectic point. So, hypo-eutectic and this is hyper-eutectic. Now, as you see that if you are coming to any composition at this point, so as you know, when you come to any temperature below this, so you will have gamma will be of this composition, and you will have liquid of this composition, because this is touching that liquidous line here. And as we see as per the lever rule, the liquid percentage will be as per the fraction of this by whole, and the gamma percentage will be by this by whole. So, this way you will have liquid and ultimately this liquid will have, at this point liquid will have the composition of 4.3%, and then this liquid will convert to the gamma plus Fe3C, that is also known as ledeburite. So, you will get that, and before that you will have the pro-eutectic, you will have austenite which is formed, and that will be coming up. Now, this what you see is this is normally the result of the equilibrium type of cooling, when the cooling is very slow. Otherwise, what you see, you can see that normally in the case of actual cooling practice, when the cooling rate is high, you will have basically the concept of coring developed, that we will discuss later, because there will be change of the concentration of the constituent, because as it is being solidified with time. So, there will be change in the concentration as we see. Now, what we see is that we have understood that in this case, when we take the carbon more than 2%, normally we call it as a variety of cast iron. Now, this cast iron is in the case of cast iron, basically the carbon which we see normally is in the form of graphite. So, what happens that when you are cooling in a slow manner, graphite is a stable structure basically. So, you are getting graphite, and Fe3C is metastable. So, basically when your cooling rate is high, you will get Fe3C, and when your cooling rate is small, you will get graphite. And when your cooling rate is small, in that case you are likely to get the graphite, and in normal case when you have a good amount of silicon and also the cooling rate is very small, in that case the graphitization is promoted. So, you will have graphite, and you will get the graphite, the type of gray cast iron, that is known as gray cast iron, because the fractured surface appears gray. So, that will be gray cast iron. So, when if you talk about the varieties of cast iron, you will have gray cast iron when you have high amount of carbon and silicon, and also low cooling rate. So, in that case you get the gray cast iron, and gray cast iron is characterized by the presence of graphite flakes. So, you will have the flaky graphite structure in the case of gray cast iron, and you have iron matrix, and the carbon is in the form of graphite. Now, if you increase the cooling rate, so if your silicon percentage is less and high cooling rate is there, so in that case you are likely to get basically white cast iron. So, if the cooling rate is higher, in those cases you are likely to get the Fe3C as that is known as combined form. So, you will be getting carbide carbon in the form of carbide. So, that is your white cast iron. It is extremely hard and normally not very much used for engineering applications, except for some cases where you need extremely high hardness, like in the case of rollers or so. Then there are other varieties also. We take into account other factors, like we use you can further use this white cast iron by further undergoing the heat treatment of this white cast iron, and that gives you malleable iron, because that Fe3C will decompose into free carbon. So, then in that case you will have small globules of carbon as graphite. So, that carbide will decompose. So, that is known as malleable cast iron. Then also we also use spheroidal graphite cast iron, that is known as spheroidal graphite iron, SG iron. So, in this case normally what we do is for the same composition, if you use the magnesium or Ce as the as it is added into the melt. So, that basically will convert this flaky graphite into the round ones. So, you get the globules of graphite and spherical globules. So, that is that is known as spheroidal graphite cast iron. So, basically if you look at so you can make it out that how at which composition how much of gamma will be there, how much of Fe3C will be there. Then further if you come down, so the gamma will again further change to alpha plus Fe3C, and this side you will have Fe3C. So, you can have the idea of the different phases formed. Coming further to the higher temperature zone, you can see one constant temperature line. There is another invariant reaction taking place here. What you see is that you will have this zone is the liquid plus delta zone, and at this point the liquid plus delta is giving you the formation of the gamma phase. Now, this is another invariant reaction, that is peritectic reaction, which is happening here at this point, and in this case the liquid plus delta is giving you the gamma. So, one liquid plus one solid phase is giving you another solid phase, and that is your peritectic reaction. So, what you see that in this iron carbon diagram, you will have different type of invariant reactions taking place. So, these are the three type of invariant reactions which we are seeing in this iron carbon phase diagram. And as discussed that depending upon the carbon percentage, you will have the usage in a different manner to the steel. So, when you come to the carbon percentage of suppose say 0. 0 to 0.3%. So, it is normally the mild steel, it is known as. And in this case depending upon 0.0 to 0.1, 0.1 to 0.2 or 0.2 to 0.3. So, they are normally known as the mild carbon steel, and you can use for the for chain links or nails, rivets, because here the ductility must be very high, carbon percentage is less. So, you will have quite good ductility. So, for them it is used. Then if it is going from 0.4 to 0.7% of carbon, so that is known as the medium carbon steel, and it will have better hardness than the low carbon steel or mild steel also, and its use will be normally in the axles, or you can have wheel rails. So, there it is normally used. And when you go from 1.8 to 1.4%, so this is known as high carbon steels, and their use is where you require higher hardness. So, you can use in the for the cutters, hammers, blades, and scissors, knives, all these are the components where you use them. Similarly, as we have already discussed that for the variety of cast iron, we use these grey cast iron where we require the damping properties. So, most of the machine beds, there we use the grey cast iron, because in that case you have the cushioning effect which is given by the graphite, which is the soft phase. And if you have to have the ductility, because when you go to the white cast iron, it cannot be otherwise used, but when you malleabilize it, when you give the annealing treatment to it, then you can use it for automobile components, because it has it develops good ductility, malleability. So, that is used. And in case of SG iron, which is found only in the cast form, it has good combination of strength as well as ductility in those cases. Now, if you take the example of the rules, like you have a tie line rule or lever rule. Now, if you try to see that if you are asked that how much pro-eutectoid ferrite. So, suppose you are asked how much pro-eutectoid ferrite in 0.6% carbon steel. So, is there in 0.6% steel that is slowly cooled. So, and also how much will be eutectoid ferrite, and similarly how much will be eutectoid ferrite. So, as you know that you will have, so you will draw the iron carbon phase diagram, and you know that this is how the reaction is for the eutectoid reaction. This is your eutectoid point, and here we know that this point on this side. So, if you go to this point, so this point is basically, you can take it as negligible, you have 0.8 here. Now, what you see is, if you want to find the pro-eutectoid ferrite. So, pro-eutectoid ferrite, now if you look at here, this is 0.8, and you are talking about this composition, that is your 0.6% carbon. Now, what you see is that you will have ferrite of composition according to this line, but ferrite's volume which is formed or amount which is formed will be based on this line upon that line. So, this is your 0.8 and this is your 0.6. So, the amount of pro-eutectoid ferrite, it will be 0.8 minus 0.6. So, it will be 0.8 minus 0.6 divided by 0.8. So, you are taking, this is very small value. So, you are taking that 0.8. So, it will be 0.2 upon 0.8 and it is 2.25. So, 25% will be the pro-eutectoid ferrite that is formed. So, apart from that, after this, so the ferrite which is formed before this point, it will be pro-eutectoid ferrite. Now, at this point you will have the formation of perlite. So, you will have rest as perlite. So, perlite will be 75%, that is 0.75. Now, you are also getting the eutectoid ferrite. Now, you can get this amount of eutectoid ferrite from this point itself, because you have ferrite here and you have cementite here. So, based on that you can get the amount of eutectoid ferrite. So, if you try to find the amount of ferrite which is formed according to this reaction, it will be basically 6.67 minus 0.8 divided by 6.67. So, that will be basically the percentage of ferrite which is formed. So, if you talk about that fraction of ferrite, at the eutectoid point, it is normally 6.67 minus 0.8, that is 5.87 divided by 6.67. So, if you take its ratio, it is normally 0.88. So, if you look at the again ferrite which is formed, that is eutectoid ferrite, it will be 88% of 0.75. So, it will be eutectoid ferrite will be 0.88 into 0.75. So, it will be 0.66. So, according to this in this way you are trying to find, this will be eutectoid ferrite and one will be pro-eutectoid ferrite. So, accordingly you can see that this will be plus. So, you will have the total ferrite which is formed. So, similar type of methods can be used for finding the different amount of different phases formed. If you come to this point or at any point, you can use these rules to find the different phases formed, and also that will also help you that when it comes to. So, basically these are the lines which talk about the reactions which are to occur after these points or after these points or after this point. So, a proper understanding of these things is required, so that when we talk about the other aspects in our course, then it will be useful and we can have more and more better understanding of all these concepts. Thank you very much.